techniques. Now, first, we should learn that how exactly the compression will take place, where exactly which type of compression take place, how different type of redundancies can be reduced. So here, if you will see, the basic model of compression is shown here. You have your original image. You want to you have your original image here, and you want to transmit it to some communication channel, right? Or you want to store it somewhere. You know that we are using our image compression for storing and transmission purpose. So if I have my original image and I want to transmit it to communication channel through wireless or wired medium, or I want to store it to my database in my memory I want to store, then I need a compression. So what I need is, I will need one encoder. This is my entire encoder, right? What it is, it includes three basic uh, components: mapper, quantizer, and symbol encoder. What is mapper? As name suggests, it maps, right? What it maps? So here, suppose I have consecutive X energy, X intensity, then consecutive Y intensity, right? Then Z intensities, right? Suppose this type of image I am having, and what will be the job of mapper? That this consecutive range of intensities, this intensities should be mapped to some function such that it will get compressed. It will be some mapping of this to some code like x2, x3. It is x occurred 3 times, y occurred 2 times, z occurs 4 times. So this is run length coding. If you remember, this is run length coding. So what exactly run length coding does? Continuous occurrence of intensity is mapped to some table, some other type of code, right? So mapping is done. The example is run length coding here. Run length coding is the example of mapping. It will map to something such a way that it will facilitate the reduction of the redundancy, mostly spatial and temporal redundancy. This is spatial redundancy, right? Is reduced by mapper. So first of all, if the image will be given to you, first of all, what you are going to do, you are going to check whether it is having any spatial or temporal redundancy. If yes, then you can simply use run length code. Okay. Then, so you know that if I have this mapping, this type of mapping, can I go back to this? The answer is yes. So mapping is always reversible. So whatever mapping you are doing, you are not losing anything here. You are simply representing this in other way, such a way that it will give you the compact information. Okay. So this is mapping, and mapping is reversible all the time. It is used for the spatial and temporal redundancy. After that mapping, you are going for the quantizer. What is quantizer? If you remember that nearby values were there, like if x, y, and z are very nearby values, by maybe the difference of 1 or 2 intensities, our eyes are not capable enough to see them. So possibly we are mapping them to some value t, right? So we are quantizing them to some value t, right? Like so that is what quantization is. Why we are doing so? Because this is irrelevant information for our eyes. Our eyes cannot see this information. It cannot distinguish between these intensities. So possibly I am quantizing them to suppose x, maybe y, maybe z, maybe t, right? So such quantization take place. But you know that quantization, suppose I will, let's see, this at 230, 231, and 232, three intensities are there, and I am quantizing them to 228. So now if 228 occurs, I will not come to know whether it is actually 228 or 230 or 231 or 232. I don't have any way to go back. So quantizer is for removing irrelevant information, and that is irreversible process. So Psychovisual redundancy is the same as as your irrelevant information. This is the other word for the same, right? And output of this will not have any irrelevant information. Here, output will not have any kind of interpixel dependencies, interpixel redundancies, and it is not reversible process here. It is reversible process here. And after that, the third step comes is symbol encoding. What it does, it removes the third type of redundancy, that is coding redundancy. Here we will encode our symbols by using variable length codes. Suppose that we have taken that 87 is one type of code. Then here, if you can recall, right, 87 was there. Yes, 87 was having one code. 128 was having another code. The probability of occurrence of 128 was higher, so that's why we were taking a smaller length code for 128. So this type of symbol encoding takes place. Symbol is 87. This is the encoding of it. So why it is used? It is used to remove coding redundancy. So all three type of redundancy is removed for the compression. So now it is not necessary that every time you have to apply all the steps. That is your choice every time that which type of redundancies you want to remove. Possibly you are just using this. Possibly you are using any combination of these three. You are maybe using all three. And then you are transmitting it to the communication channel. Right. So what is the goal of the quantizer? Quantizer's goal is to keep irrelevant information out of the compressed representation, and it is irreversible. Right. And if you want that you want totally lossless compression, then this step must be omitted. Otherwise, it will not be lossless compression. Next is symbol encoder. So that is for the what is the frequently occurring output values will have different codes than the less frequently occurring codes. That's why it is removing the coding elements. So these are three steps. So now output of this mapper, quantizer, and symbol encoder is given to output will be compressed data, and it is used for the storage and transmission, as I told. Okay. Now at the receiver side, or while retrieving the image, what you have to do? While you retrieve, you will get your codes only 0, 1, 1, 0. You will not have like 87, 128. You will not have those values. You will have the binary value 0, 1, 1, 0 kind of things, right? So what you have to do? First of all, you have to reverse the process of symbol coding. Suppose it is 0, 1, that means it is 87. Suppose it is 1, that means it is 128. 128 was coded with value 1, right? So that type of decoding is required. Now, whatever coding method we have, according to that, depending on that coding method, decoding mechanism works. We will see many coding mechanism now onwards. We will see, and we will see their decoding mechanism as well, right? So decoding is required. Is it fine, or should I arrange something else as well? Is it fine? Is it audible? Okay, let me know if further it creates problem. Okay, and further is inverse. Okay, then this process is reversed. Now we have to go for this process reverse. So actually, I want to go for all the process in reverse. But I know that if I will quantize it once, I am not able to reverse it at all. There is no meaning of reversing this because it is not possible to reverse it, right? So that's why this step is omitted. This is not possible to reverse. That's why it is not needed. But whatever mapping is done, like x 3 times. So now you need reverse mapping, that you, instead of writing x3, you will write x, x, and x. Run length mapping, whatever you did, in the reverse way, you will make it as regular image. So this is very basic compression model. So here, one thing comes in our mind that possibly one image have all kind of redundancies, and you may try to reduce a certain kind of redundancy, or you may try to reduce all type of redundancy as well. That depends what kind of output and what kind of processing capability your devices have. Now, now we will start with Huffman coding. It comes here. It is the method of symbol coding. Now we will assign code word to symbols. Actually, it is variable length coding. It will assign the optimal code. It will try to minimize the number of bits per symbol. Or rather, we should say more probable symbol is there, the less number of code length is applied, and less probable symbol is there, then it more length can be larger one. Here symbol in our case is pixel value. Okay, so now what is the methodology? Suppose the probabilities are given for uh, six symbols. The A1's probability is 0.1, A2's probability is say 0.4, A3's probability is say 0.6, A4 and 5 are given like this. So probability. So what is what is the given thing here, that I will have six symbols A1 to A6, and their corresponding probabilities are given here. In our case, so even if you want to think, you can say our symbols are 0 to 255, and probability of occurrence of 0 to 255 we know how to obtain from. Is it audible now? Is it fine? If it is creating issue, let me know. Okay. Assuming right now it is not problematic to you, let me know in case it creates problem, right? Okay. So now in our case, in our image, what is given here is six symbols are given A1 to A6, and a probability of occurrence of A1 to A6 is given. How you will see this in our image case, that we have symbols from 0 to 255, or my probability, my value of my pixel can take place from 0 to 255. So I have 0 to 255 symbols, and probability of occurrence of 0 to 255 I can easily obtain from histogram equal my normalized histogram. Okay, here what is the meaning? Here in my message A1 to A6 can take place anytime. What is the probability that A1 will take place in my message? That is, it is 0.1 time, a 0.1 probability, which that is 10% of the time in my message A1 will take place. That is what the meaning is. So in my image, you know that 0 to 255, possibility of the symbol occurrence is 0 to 255, and what exactly the probability will be that you can get from the normalized histogram. So right now I have this information and its corresponding probability of occurrence. Right now, what is Huffman coding? So first step of the Huffman coding is that you have to arrange your symbols in the descending order of the probability of occurrence. So you have to sort the probabilities, right? And you have to combine. You have to combine lowest probabilities first. So what you will combine? So here the probabilities are arranged in descending order, and lowest two are combined. So what is the combined value here? It is 0.1, 0.6, 0.06 plus 0.04, that is 0.1, right? Okay, then you have to repeat the step till only two probabilities remain. So now what was the last step? That combined lowest two. So these two are combined. So now what is this the summation value? Summation value is 0.1 plus 0.1. That is 0.2. 0.2, and so 0.2. But 0.2 if I will write here, then this order will be not in descending order. So I have to manage the descending order of the probability as well. That's why this 0.1 and 0.1 uh, is kept here, right? That the summation is kept here, and this 0.1 came here because I have to maintain the descending order of the probability as well, right? Same way again, so again still multiple probabilities are there. They are not just two. So again I have to repeat the step two. What is step two? Combine last two. I have combined last two. So last two is 0.2 plus zero point 0.1, that is 0.3. What is earlier value? It is also 0.3. So if I will keep my 0.3 here, it will still remain in descending order, and that's why I will continue with that. Are there only two probabilities? No, there are not only two probabilities. That's why I can um, so I can to continue with the second step. What is the second step? That I combine last two lowest probabilities. So last two lowest probabilities are combined. The value is 0.6. 0.6 is, if I will write 0.6 here, it will not be the descending order, and hence I have to change the order here, and I have to write it like 0.6 and zero point 0.4. Now, are there only two probabilities? Yes, there are only two probabilities, so now I have to stop. Okay, so in that way, we created a tree here. Right? Now, what is our next step afterwards? We will start assigning 0 to higher value and 1 to lower value. 0 to this and 1 here. Right? So now, so this is 1. That's why this is uh, uh, here you can see. Here I assign 0 and here I assign 1. Right? So that one is actually here. That will go. That one is assigned to this 0.4. That one is assigned to the same 0.4. So let's say that one is assigned to same 0.4 and that one is assigned to same 0.4. So that you keep in your mind that we have assigned the code 1 to this this 0.4. Right? Now 0 is assigned here. Right? So that 0 will actually is assigned to combination of these two. So that 0 is kept in MSB and LSB is again assigned 0 and 1 to these two values. Right? Now then okay, so 0 is assigned to upper value, 1 is assigned to lower value. Okay. Now, so now that means 0 is assigned to this 0.3, that is 0 is assigned to actually this 0.3. Okay. Now what will happen? Now we have 0.3 here. 0, 1 is assigned to this 0.3, but this 0.3 is actually combination of this 0.2 and 0.1. Okay, so that 0, 1 will get propagated here and it will be the most significant bits. They will be most significant bits. And now upper value will be, that is higher value will get assigned 0 and another value will get value 1. So the third bit I have to add, but higher value will get 0 and lower value will get 1 here. Okay, so so that's why this point one, point one got 0, 1, 1, and that point one was actually present here, and that point one was also present here. Okay. So and this 0, 1, 0 was actually the combination of this point was assigned to point two, and this point two was actually the combination of these 2.1s. So this is actually we are doing this backward pass. Okay, and whatever the probability, whatever the code is assigned to this combination, that is kept is assigned to the summation, that is kept as MSP, most significant bits. Okay, and then upper value is assigned extra LSB. It is higher value will get 0. If they are equal, then upper value will get 0, and lower value will get 1, or higher value, because it is descending order. So every time if I am assigning 0 to higher values, then it will higher I mean 0 to upper values, then always higher value will get 0. So in that way, I have assigned this code to point 1 and this code to another point 1. But again, this point 1 was from this, and this point 1 was the combination of these two probabilities. It was the combination of these two probabilities, and hence what will happen? What will happen? The 0, 0, 1, 0, 1, 0, 1, 0, 1 will come to MSB, and again 0 is assigned to this probability and 1 is assigned to this probability. Now, if you will observe, now we have the codes. We have the codes for every symbol. That A2 will have code 1, A6 will have code 0, 0, A1 will have code 0, 1, 1, so on, and A5 will have code 0, 1, 0, 1, 1. Here, if you will observe, the probability of A2 is highest and length of the code is lowest here. And probability of A5 is lowest and code word length is higher, or we can say highest here. Here both are very less, so we have used more number of bits to represent the symbols with lower probability. So two steps of the Huffman coding. First is forward pass. What to do in the forward pass? All possible symbols are going to list in the descending order of the probability. They are going to combine the least, last lowest two probabilities. You are going to combine, and in that way you are going to create the tree. By creating tree, you just keep in your mind you are maintaining the probability in the descending order here, and then you will do the backward pass. Assign 0 value to upper one and 1 value to lower one, right? And if your assigned probability is having it is made up of combination of few probabilities, then whatever code you have assigned to that probability should be taken as MSB, and further should be taken as MSB, and further 0 and 1 should be assigned as LSB. Again, 0 will be assigned to upper value, 1 will be assigned to lower value. In that way, you are going to repeat the entire process. And this is what Huffman coding is. Okay. Now, what is the case? Like we have to check that what is average length we obtain. What is the average length? How many bits per pixel I obtained? How many bits per pixel I obtained? It is to represent a pixel. How many bits I am using now on an average? Otherwise, if my pixel value is A2, then I am representing it 1 bit only. But if my pixel value is A5, I am using 5 bits to represent that A5 pixel value. But on an average, how many bits per pixel I am using? So for that you know what is the formula? That the length and probability of occurrence of that length. So length is 1 and probability of occurrence of length 1 will be whenever A2 will take place. When A2 will take place, what is the probability that A2 will take place? 0.4. So what is the probability that length 1 will take place? 0.4 times 1 is going to take place. How many times 2 will take place? Length 2 will be there for the pixel. So we can say a number of times A6 will take place. That many times I have to represent that A6 with 2 bits, and hence 0.3 times A6 will take place, and hence at 0.3 time I am going to use this 2 bits to represent my pixel. Right? In that way, if we will repeat for all, so what will happen? That for length 5, the probability is 0.4. For the length 5, okay, so we are going slow here because maybe here the case is, service is slow maybe. Okay, so the only thing that we can do is I can explain you by the words and we can go a little slow. Right? Possibly, I will, instead of showing through the symbols and arrows, I will speak it and we will go a little slow. So that is how it can help. Okay, so fine. So we can repeat here. What I want to know is that how many beats, what is the average length of code word? That is what my requirement is. So what exactly will happen? Suppose my requirement is to find out average length of code. Otherwise, what happens if A2 occurs in my message? I'm going to use 1 bit to represent that code. If A6 occurs, I'm going to use 2 bits of length to represent that code. If A1 occurs, I'm going to use 3 bits. That is fine. But what is on an average length of my code ever? right? So for that, how will we know? So whenever A2 occurs, right, I'm going to represent it using what? That is how many times I'm going to use my code to code length 1 to represent my code. So number of times A2 will take place, that many times I will use length 1 to represent the code. How many times A2 will take place? So we can say 0.4 time A2 is going to take place. Right? So 0.4 time of the total time, or 0.4 of the total symbols, 40% of the total symbols, A2 will be there, and to represent A2, I'm going to use length 1. So what is the probability that I am representing my code word with length 1? So I can say 0.4 times I am representing my length of code as 1. Okay. Now next is how many times I'm going to use length 2, that is 2 bit 00. So number of times A6 will take place, that many times I have to represent it with 00, that is length is 2 now. How many times length will be 2? Number of times A6 will take place, that is the probability 0.3. 0.3 times or 30% of time A6 is going to occur, and I'm going to represent it A6 with 2 bits. So totally 30% of total time I'm going to represent the code word with length 2. So what is, in that way you can repeat for all. Right? So what is the average length of code? So we can say that the length of the code into probability of occurrence of that length. So length of the code is 1 and probability of occurrence of that length is 0.4, plus length of the code is 2 and probability of occurrence of that length is 0.3, plus length of the code, which is 3, into probability of occurrence of that length, which is 0.1, plus length of the code is 4 into probability of occurrence of that length is 0.1. Length of the code 1, 2, 3, 4, 5 is 5. And probability of occurrence of that length, how many times this length is going to take place? So it is 0.6 times. In that way, so what is that? Observation into probability of occurrence of observation. That is length into probability of occurrence of that length. And that will give me the average length. Okay. So in that way, if you will check, so 3 into 0.1, so that the probability that length, the probability of occurrence of that length. So in that way, if you will sum it them up, so total answer is going to be a 2.2 bits per symbol. So you are using actually 2.2 bits per symbol, right? And if you are not applying this methodology, if you want to represent 6 symbols, suppose I am not doing this, but in my message A1 to A6 takes place, and I don't know about this Huffman coding, and I'm not doing that. So what I will do, to represent A1 to A6, I will need 3 bits. Suppose I'm representing A1 with 000, A2 with 001, A2, A3 with 010, so on. For A6, 110. Right? So if 110 occurs, I will understand A6 takes place. Right? So in that way, what I'm doing, if I'm going with the regular method that I'm used to, then I'm using 3 bits per symbol, A1 to A6 for A1 000, A6 110. So by using Huffman code, you can see per symbol required bit are now 2.2, and that is reduction in bits, requirement of bits, right? And that is what shows that compression takes place, right? So instead of in our image having 0 to 255 value, in our image we will have A1 to A0 to A255. Our intensities can take place 0 to 255 values. So if I'm not doing anything, I don't know about Huffman coding or anything. So what I will do, because it is having 0 to 255 values, that is 256 values, so I will need 8 bits. But if I'm going with this type of Huffman coding, the required number of bits per pixel, which is 8 earlier, will reduce. And this is how I can achieve the compression. Because of voice cracking and maybe delaying the screen, are you comfortable about this code, or should I repeat anything here? Are you comfortable with Huffman? Are you comfortable with Huffman? Should anything be repeated here? Because examples you will not be comfortable, otherwise I can repeat the method if you want. Anything? Are you clear with it? Should I repeat? Kindly answer. Should I repeat? If you need, I can repeat. Okay, that's good. So now, so how? So fine. So I have the coding now. Like I have A2 if occurs, then I'm going to use one. So in my I have the codes now. So now if A1 occurs, A2 occurs, I'm going to use this codes. And this is transmitted. How receiver will come to know. So decoding, that is decoding, or how while retrieving, how we will get our original values back. That is retrieving. So decoding is required when received or retrieved. The pixel is, the image is received or retrieved. So decoding here, it is very simple method, that is lookup table. You need that A1 will be represented by C. What will happen? You will need this type of table. You will need this type of table. If suppose this is the value that you are receiving 0 1 0 1 0 0 1 1 so on, right? These values are received. Then you will check. Do I have any symbol with starting with 0? So I will check. Only 0. Do I have any symbol having is represented by only 0? So answer will be no. There is not a no symbol which is just represented by 0. Right? Okay, so it is not the only symbol. Then I will go for the next 0 1. 0 1. Do I have any symbol which is just represented by 0 1? So here you will see 0 1 is having here. We are having 0 1 here, here, and here. So possibly these two are not my symbols, right? Fine. Then we are going for, but I don't have any symbol which just having value 0 1. So I have to go for the next value as well, next bit as well. It is 0 1 0. Do I have any symbol which is just represented by 0 1 0? So answer will be 0 1 0 is available in 3. So possibly this 3 can be, any of these 3 can be your answer, but not at least this, because it is having 0 1 1. Okay. Then you will go for, okay, but I don't have any symbol which is ending with 0 1 0. So I will go for one more. Then 0 1 0 1. So of course this is not my symbol. Possibly any of these two is my symbol. And then I'm going with further 0. So I will come to know, okay, I encountered a symbol which is having the value, desired value 0 1 0 1 0. That symbol is A3, and hence this is A3. I encounter, okay, yes, I have a symbol with 0 1 1, that is A1, and that will stop here, and then again I will start with this. Here it is 1. Do I have any symbol that start with 1? Yes, we have, and that's why it is A2. And again, so I will start for this from the beginning again, and this is how decoding takes place. So this type of table, this type of tree is not only created at the transmitter side, but also it is created at receiver side if you are transmitting the image. This must be known to receiver, that what is the probability of occurrence of intensity, what is the probability of occurrence of symbols, may not be the order. So do you want to get repeat, anything should be repeated here? What is your point here, Vivek? Okay, so what we were discussing here, that's all right. If it is some case was urgent, you can of course take a break little break, small break, that's all right. In anything, if you want to get repeated, I think you will fall. But yeah, it will be clear to you because you are taking more examples, so it will not be problematic, right? Fine. So now, what is the case? So this is, so whenever if you are transmitting something, right? You are transmitting the suppose you are transmitting your image or you are transmitting your message, right? If you are transmitting your message, then this must be already known to you and your you and your receiver, that what will be the probability of occurrence of your symbols. That's why this type of tree is created at your receiver, or otherwise you have to transmit this table along with. Okay, that is the only way that you can get your code back. But generally, this is possible to transmit as well, to transmit the probability of occurrence of the what you can say symbols, and that is how retrieval is possible. But another problem with this code is what? Suppose suppose this 0 changes with 1. Possible while retrieving it from the memory, or bad memory issues, or because of we are transmitting the channel noise. Suppose this 0 alters to 1, right? So what will happen? That this one will be treated as a separate symbol A2. Simple 1-bit error occurred, and that is very common. 1-bit error is quite common. So then this will be detected as A2. This will be detected as A2. This will be also detected as A2 now, and this will be detected as something like 0 1 0 0. So it will be detected as A4. This will be detected as A4, and so on. Then again A2 A2, so on, right? So this will total, just 1-bit error can ruin your message total. And that is what the problem with Huffman coding is. Single bit error can ruin your entire message. I hope you can understand that thing here. Right? So now if you want to have this example quickly, then tell me what is the message decoded here. Be quick, this is the table. Tell me what is the message decoded here. So what is the first symbol? What is the first symbol? Zero one 0 1 0 1 0. 0 1 0 1 0. So that is the first symbol, that is A3. Then next is, what is the next symbol? Next will be A6. Yes, next will be A6. Then for the next will be again A6, true. Then next will be, so we have A3, A6, A6, and A6, A6, then A2. Yes, A2. It should be A2. Yes, it should be A2. Because it is 1, so it is A2. True. Then A3. A3. Okay, so we are to A3 or 5? 0 1 A5, na? A5.
Okay, A5. So we are going for A5. Then where we are at A5 up to this, then A2 for this, A5, then A2 for this, then A2 again, and A2 again. Up to this are A2, A2, A2. Then next is, last is A1 or 4, 4, 7, 1 or 4, 0, 1, 0, 0, A4, na? This is what. So what our symbols are if you want to check? A3, A6, A6, A2, A5, A2, A2, F. These are the symbols, decoded symbols. Okay. Now quickly complete the example for this. What is that? Compress this image using Huffman coding. Compress this image using Huffman coding. This image, this I told you that multiple times we are going to use this image. And compute the compression achieved and effectiveness of Huffman coding. That we will see how to compute, but quickly compute it. Compress this image using Huffman coding. How will you compress? So first of all, you have to find out probability of occurrence of symbols. How many symbols we have? Only 4 symbols are there. 21, 95, 169, 243. Then count the probability of occurrence and arrange them into descending order. Then combine the lowest and assign the codes. So if we go for probability of occurrence of, I think 21 and 43, we have the highest one. And then we have 95 and 169. You can arrange them according to your record. If they are equal, then you can have 169 upper and then 95 lower. That is your choice, right? Because they are equal probable, so it will not make sense, make difference that you are one will get lower or higher number of votes, right? So probability is required. Last time you calculated, I hope you have that calculation. If not, then quickly calculate and let me know. This is 84 cross 8, that is 32 intensities. And 12 intensities out of 32 are 21. So 12 by 32. Then 4 by 32. No, again 12 by 32. Then 4 by 32. And 4 by 32. Now combine these two. So tell me what is the combination of these two? It will be 8 by 32. And 12 and 12 by 32. Then what to do? Combine these two. What it is? 20 by 32. So 20 by 32 is higher than 12 by 32. Okay, assign the codes now. Tell me what is the code for 21, 2, 43, 95, and 69. Give me the codes. So what is the code for P21? What is the code for 21? Yes, for 21 it is 1. We are assigning 0 here and 1 here. That is 1 here and here. Then this 0 is acting as MSB here, 0 and 1 here. Then 0 and 1 here. For this I am writing it, right? Please understand that. And that 0, 0 will come here. And this, sorry, 0, okay, this will be 0, 1. And this 0, 1, 0, 1 will come here. And 0 with this and 0, 1 with this. Yes, 169, 0, 1, 1, 95, 0, 1, 0. Okay, fine. Now, how much compression you have achieved? How will you calculate that? So what you will do? What was the earlier requirement of how many bits you were earlier requiring? So you were having 32 pixels and you were requiring 8 bit per pixel. Right? So earlier you needed that 32, that is 4 cross 8 into 8 bits. Totally this many bits are needed. Now for pixels are same, I have not reduced pixels, so pixels are 32 only, but per pixel, how many bits I am using? I am not using 8 bits. For 21 I am using 1, for 243 I am using 0, 0, for 95 I am using 0, 1, 0. So that means I have to calculate how many bits I am using per pixel. If I will substitute that value here, then I am going to get the compression ratio. Earlier per bit, per pixel 8 bits. Now per pixel, average number of bits are required this, and hence the compression achieved is this. So tell me first, find L average. You know how to find out. Length of your code word into probability of occurrence of that length. So calculate L average. What is L average? I should do that. Vivek? It is 1.875. We are getting 1.875. Good. So we are getting, so what is the meaning here? That I am using 1.875 bits
per pixel. So if one pixel is represented on an average 1.87 bits, so 32 pixels are represented by this many bits. So what is the compression ratio that you have?
What is the compression ratio? Just 8 divided by 1.875. No? Who will quickly and let me know? 4.26. 4.267. Good. Now, so that is what the compression achieved is 4.4 times 4 by the factor of 4. You have achieved the compression that you can see now that earlier the on average 8 bits were required. Now 1.87, that is we can say 2 bits, and that you can see 4 times compression is achieved. Okay, so compression achieved is 4.2 by the factor of 4.267. You have achieved the compression. So that is one equation. One question is solved. Now next question is
the effectiveness of the movement coding. How to calculate that? So what exactly they want to ask, that how nearer this is to the ideal compression value. How much ideal compression is possible
and how much close to your compression is to that compression. So how do you come to know that what is ideal compression ratio? So the thing will be the same, that original, this is the requirement, but best compression is possible by, if you will substitute the value here, which is given by entropy. What entropy gives? That how much information your each bit contains, right? If you are suppressing lesser than that, that means you are losing the information. That many bits at least you have to use, right? So entropy gives you that how much information per pixel you have. And if I'm substituting that value here, that this is the minimum information, that this many bits are required to represent information in my pixel, that is minimum bits required. If I substitute that here, whatever compression ratio I am getting for that value, and I can compare that value with this, and I will come to know that how much effective this method was. So for that, in short, what I will need, that how many bits per pixel ideally I should have. And that was, yes, entropy was 1.811 in the last example we did, but if you want to calculate, you can calculate it again. Yes, it was 1.811, and here you can see you are getting 1.875, which is near to 1.811, but it is lesser than, because it is not the ideal value, right? So it is near to that. So now you will substitute 1.811 value here, and you will get your compression ratio. What it is? 4.417, and find out what is the percentage. This value is how much percentage of this value. This value is how much percentage of, how many percentage of this value. If 4.417 is 100%, then this is how many percentage? 5%. It is this divided by this, divide to 100. Compare this to in terms of percentage. That this value is how much percentage of this. What is your answer for that? How to obtain it? This is if this is my 100%, then 4.267. No, 3.4. You took subtraction. I don't know the difference here. No, don't subtract it. But actually, what I want is, if this is 100%, this much is how much? Because this is the maximum that I can get. How much I obtain? This much. So whatever I obtain is how many percentage of the actual one or ideal one. Understood? So what you have to do, you have to subtract this 3.4 from the 100. So that, I hope you are getting the point. Otherwise, what you can take is 4.267 divided by 4.417 into 100. Do this. Yes, and that is what, 96.6 or 9, 96 point something, right? So what is the meaning? What we have obtained 96% of the possible compression. This is what the effectiveness of first-line coding is. We have obtained 96% of the possible compression. That is good, really good. So possible compression, we have achieved 96% of it. Okay, so this is all about Huffman code, and this is what 96.67% of compression we have removed. So what we actually what is conclusion here, that just we remove the coding redundancy. Here we have not gone through any spatial, we have not applied the journal encoding or any relevant information. We have not removed. Just by removing the coding redundancy, we compress it to 96%, and it is huge amount. It is huge amount, right? So this is very effective way. Now next method will be arithmetic coding, but here we cannot start. In the next lecture, we'll start with the arithmetic coding. So we have to stop right now. Any doubt in case you have anything that you want to discuss? Are you comfortable with Huffman? Any doubt? Okay, so in the next lecture, we'll start with arithmetic coding. And we are stopping our discussion now. We are concluding our discussion. Okay, so we will meet in the next lecture.
Good afternoon, everyone. Am I audible properly? Good afternoon, everyone. Am I audible properly? Please reply. Okay. Okay. So, listen, everyone. Today's lab is lab number 9. The aim of today's lab, that is knapsack problem by using genetic algorithm. Today's aim is knapsack problem by using genetic algorithm. I'm sharing my screen. screen is visible to you, everyone? Hello? Is it visible properly, everyone? Hello? Okay, okay. Okay, let's start with the lab. Now listen, today's topic is knapsack problem by using genetic algorithm. Now, see, all of you know the knapsack problem, right? Um, See, here, first of all, I will explain you the concept. See, here item is given, weight and value is given. So there are four items and each item is associated with the weight W and the value at item B. Okay, so there are four items and each item is associated with weight and value. Now please write down everyone this weight and value. So when the calculation is done, so at that time you can understand. See, I am waiting for 2 minutes, everyone. Please note down this weight and value. Right? So in the calculation, it will be useful to you, everyone. Okay, so listen, there is an knapsack K with limited capacity that can hold almost 12 kg. So here the capacity is given, the knapsack capacity is what? The knapsack K with the limited capacity that can hold almost 12 kg. That you have to remember. Now what is the problem? The problem is that which item should be kept in a knapsack so as it will maximize the knapsack value without breaking knapsack. Again I repeat, the problem is that which item should be kept in a knapsack so as it will maximize the knapsack value without breaking knapsack. Okay, so this is the problem. Now, now listen everyone. In this genetic algorithm, all of you know the steps. The first step in just wait everyone. Hello. So listen everyone, in genetic algorithm, all of you know the steps, right? In genetic algorithm, which are the steps that you know everyone? The first step that is population initialization. Then the second step that is fitness function calculation. Okay. Now then after first the population initialization is there, it is done with random initialization is done. Right? In genetic I have explained. Then after the fitness function is calculated and based on the fitness function then selection is done. And in selection we are using what? Roulette wheel selection method. All of you know that in theoretical that portion that we have explained. Now once the selection is done, then after the crossover is applied. Then after the crossover, the mutation is applied. Mutation is optional. If you want to apply, you can apply. Okay. Now now see the process is repeated until some termination criteria is satisfied. Up till now, this process is continue, and once the condition is satisfied, then after the termination is done. Right. So these are the steps of genetic algorithm: population initialization, fitness function, then after selection is done, then after crossover, then after if mutation is required, then mutation. Okay, so these are the steps for genetic algorithm that we have discussed earlier. Now, see here for population initialization. See here, I can say that all of you know that. See, suppose I want to in population initialization, random initialization is done. But see here in this case, I told you that there are different way for representing what the chromosome, right? One of the way that we have discussed, that is in last lecture that I have discussed, by using 0 or 1 means in that way you can represent. Another representation is by using array you can represent, right? There are different way in means according to your problem you have to represent the chromosomes. So now here in knapsack I am using I am considering an array CI that represent all items together. Now see, I will explain in this way. Why? Because when you implement it, so at that time you can represent the chromosome in this way. Means you can declare the array like this, or array means whatever the approach. But see, I am showing you this approach. By using the array, you can show. Sorry, you can represent the chromosome. Now see, here all of you know there are 4 items A, B, C and D. Right? So this is my array. So here I can say that the 0 represents the absence of item in the knapsack and 1 represents the presence of item in the knapsack. Okay. So 0 represents the absence of item in knapsack and 1 represents the presence of item. So here there are 4 bits. So that means the 4 bits are requested to represent the chromosome encoding. That is, the space is 2 raised to 4. The space is 2 raised to 4. Right. So the initial population is created and the chromosomes are randomly created. Okay. But see, right now I am taking only 4 chromosomes. Right now I am considering only 4 chromosomes. Okay. So for easier calculation, right now I am taking only 4 chromosomes. Okay. Now, see here in this case, I can say that see C1 is one array. So here the first 0 that represents the absence of item in knapsack. 1 represents the presence, 1 represents the presence, and again the 0 represents the absence of item in the knapsack. Okay. Similarly, the C2 is randomly generated, C3 is randomly generated, and C4 is randomly generated. So these my generation 1. Listen everyone, this is my generation 1. So randomly this population is generated. Okay. So the first step, that is population initialization, that is this is the first step of genetic algorithm. Now, hello, am I audible properly everyone? There are some network issues. Please tell me everyone, am I audible properly? Okay, thank you. So this initial population is done everyone. Population initialization is done. Now then after that, what is the next step? So the next step, that is fitness function. Okay, so this is step number 2, fitness function. It to determine the fitness function which is used to evaluate how good a particular solution is. How good a particular solution is. Now see, let's say I am taking the C1. Okay, so here total what? These are the 4 populations, C1, C2, C3 and C4. Let's say I am considering the C1 population. So here I can say that it represents that the knapsack has presence of item B and C and absence of item A and D. Okay, so right now I am talking about C1 everything. So now here how to calculate the fitness function value? So here the 2 things I am calculating. One is the value of the knapsack and another is for fitness I am calculating the value as well as I am calculating the fit. So now see here in this case in C1 it is 0, 1, 1, 0. That means which 2 items are present in knapsack? B and C. Now see here. So here only B and C is present. So what is the weight? The weight is, see this is 0, 1, 1, 0. So that means only these 2 items are present. So weight is 3 plus 7 means 10 in C1 and the value is 5 plus 10, that means 50. So the value is 5 plus 10 means 50, and the weight is 3 plus 7, that means 10 kg. Now see, the initially you see that there is some knapsack capacity is given, right? Here it is given. The problem, see, there is an knapsack K with the limited capacity 12 kg is given, and here what you get the answer, everyone? Here the weight you are getting, weight you are getting, that is 10 kg. So the knapsack capacity is 12 kg. So as 12 kg is greater than 10 kg, that means you can say that the population C1 is accepted. Similarly, you have to check for C2, C3 and C4. Now everyone check for C2. So what is the C2? So C2 is 0, 1, 0, 1. Okay, so 0, 1, 0, 1. Now can anyone tell me the answer? See, 0, 1, 0, 1. So that means here you can say that the weight is what? 3 plus 2, that means 5, and 5 plus 7, that means 12. So this thing you are getting 5 and 12, everyone. So now see, the capacity is 12, that one, but here weight you are getting 5. So that means C2 is also accepted, everyone. Similarly, check for C3, everyone. So C3, that is 1, 1, 0, 1. So 1, 1, 0, 1 means, see that. So this is 1, 1, 0, 1. So that means 5 plus 3, 5 plus 3, 8, 8 plus 2, 10. Similarly, the value is 12 plus 5, 17, 17 plus 7, that means 24. Okay, so here you are getting what? 10 and 24. So also here you can say that, so this is 10, but the maximum capacity is 12 kg. So C3 is also accepted. But you see here in the C4 all are 1. So here you are getting 17 and 34. But the knapsack capacity is what? 12. But here you are getting 17. That means you can say that the C4 population is discarded. So here only 3 population is considered: C1, C2 and C3. Based on, because according to the, because knapsack capacity is given, based on that when you calculate it, so this 70 is more than that. That's why you can say that this C4 population is discarded, only the C1, C2 and C3 is considered. All of you clear up to this? Hello? Jaimin, Jai, Mahesh, all of you clear up to this? Anyone have a doubt? Okay, so I think all are clear. Now continue with the next. Now listen, this is the fitness function. Okay. Now this is second step, fitness function. Now after the fitness function, what happened? Now the next step is selection. The next step is what? The next step is selection. So here in this case you can say that the selection means the next step is to collect the filtered individual and wake up the next generation chromosome. So here I can say that by using, so in selection I told you that in relatable selection we are using. So in relatable selection, all of you know that what you have to do, spin the roulette wheel, and whenever the wheel is stopped, the individual gets selected at that point. Okay, and the individual that has the highest fitness value gets a largest share of the wheel, gets the largest size, or you can say largest share of the wheel. Okay, so here I can say the total fitness value. How I have calculated the total fitness value? So see, this 15 plus 12 plus 24 plus, here why I have considered 0? Because see, the C4 is discarded, right? Because the knapsack capacity is 12, but here it is 17. So only for value, knapsack value is 15 plus 12 plus 24 plus it is what? 0. So that means the knapsack capacity, so the total fitness value we are getting, that is 51. Now see, the fitness value of C3, that is 24. All of you know that. Okay, the fitness value of C3 is what? C3 is 24, everybody. Now, so here you can say that the fitness value is C3 equals to 24, means it's the largest fitness. So the C3 occupies the half of the weight as 24 divided by 50. And C4 has the 0 chance of winning, and the C3 has the highest probability of getting selected in the next generation. So see this roulette wheel. So now see C1, C2 and C3. The C1 here getting 15 divided by 51 in C2. So out of 100 you can say that the C1 occupies the 15 divided by 51 this much slice. The C2 occupied the 12 divided by 51 slice. And the C3, that out of 100 the C3 get 24 divided by 51. So this much slice the C3 get. Means from this we can say that the C3 occupied the half of the wheel, means the largest witness the C3 is occupied. Okay, now after all of you know that after spinning the roulette wheel, see suppose the first time I am moving the roulette wheel, so at that time let's say the C3 will be selected. Normally what happens, whoever more fitness, there is a more chance of selection of that particular population, right? So here you can say that when I spin the wheel, so let's say my wheel stop at C3. Okay, so initially let's say I am selecting first of all C3 will be selected first. Now suppose let's say again when I move the wheel, so at that time next it will points to C1. Then after again I move the wheel, then let's say C3. Then again it may see the same population may also be occur, because when you are moving the wheel, right, so at that time wherever it stop, that particular population that you have to consider everyone. Okay, so first C3, then C1, then C3 and C2. So now what happened? So in the next generation you can say that C3, then when I again move the wheel, then C1 is selected, then again move the wheel, then C3 is selected, then again, so let's say it stop at C2. So this is my generation 2. This is my generation 2. Anyone have a doubt up to this? Hello? Anyone have a doubt up to this? Please reply. Clear everyone? Okay. Now, so up till now we have learned population initialization. Then after we have seen what after the population initialization, fitness function we have calculated. Okay, fitness function we have calculated. Now after the fitness function, you can say that selection is done. Right after the fitness function, now selection based on the relative selection it is done. Okay. Now see, now after this four populations are selected everyone. After this, these four populations are selected. Now the next step is crossover. So in crossover, what you have to do? The crossover operation takes the selected chromosome. So any pair, the crossover operation takes select for what matching, and mixes the genetic material to produce the offspring, right? So in crossover, what happened? So any two chromosomes are selected for matching and mixes the genetic material to produce the offspring. Now, suppose, listen, out of this four population, suppose let's say this C3 and C1 I am considering for mating. Okay, suppose let's say first true I am considering. So, this first true C3 and C1. These two I am considering everyone. So, in C3 chromosome, in C3 chromosome it is what 1101, and C1 population that is what 0110. Okay. Now all of you know that after writing this, now all of you know that in either you can apply 1 point crossover, or you can apply 2 point crossover, or you can apply uniform crossover. Any you can apply. Next I am applying the 1 point crossover. Now in 1 point crossover, all of you know that it randomly selects the position on the chromosome about the gene would exchange. Now let's say see here one black line I have drawn. So this is my crossover point. Okay. So after the crossover, what will be my result? So all of you know that the date of parent one. Listen, what is your offspring one means the first child that is the head of parent one that is combined with the tail of parent two. Similarly, the head of parent two that is combined with the tail of parent one. Right? In that way it is combined. All of you know that. So what is your offspring one means child one, that is 1100. See that 1100. And what about the child two, that is 011, and this that means 1. So 011. Okay, so suppose child 1 I am denoting as a OS1, and offspring 2 that I am denoting as a OS2 everyone. So now see, here you can say that, see, before crossover it is what, C3, C1, C3, C2, all of you know that, right? But after the crossover, now what happened? See, here we have applied C3, C1. So now after the crossover, what happened? The OS1 will replace C3 and OS2 will replace C1, and C3 and C2 do not go for the crossover. So it will, so they will remain in the next generation or everyone, right? So this is the result before crossover. But after the crossover, what? After the crossover, see here, nothing you have to consider. So after the crossover, it becomes OS1, OS2, C3 and C2. Okay, so this is the result after crossover. Everyone. Now, after the crossover, the next step, that is mutation. Now, all of you know the mutation. That is, mutation means it's providing the diversity within a population, so that the search algorithm does not necessarily get stuck at the local maximum. Now, see, also I explained that, see, the child inherits the characteristic of the parent, but child have its own characteristic, right? So yeah, that's why in that terms you can also say that the mutation is performed. Okay. Now, with some probability you can do the mutation. So now see, after the crossover means before mutation, these are the results. Everyone, you know that OS1 means you can say that this is 1100. OS2 means 0 triple one. Then what is C3? C3, that is 1101, and C2, that is 0101. Okay, so this is the result after crossover means, or you can say that before mutation, or you can say after crossover. This is the result. Now, suppose listen. Let's say this 2-bit I want to mutate. Let's say this 2-bit I want to mutate. So all of you know that in mutation, if 1 is there, then 1 is changes to 0, and if 0 is there, then it is changes to 1, right? So in that way it is done, everyone. So here, so after the mutation, what happened? This 1 is changes to 0, right? In this underline. So after mutation, what happened? OS1 becomes C0100, right? And OS2, that becomes 0011, and the remaining two, C3 and C2, that remain as it is, everyone. Okay. Now, so mutation is the last stage of this generation. Now after that, what happened? After the mutation, again you have to calculate the fitness, everyone. Once the mutation is done, now listen, the mutation is not compulsory. Suppose if you don't want to perform the mutation, then what happens? After this crossover, you have to calculate the fitness value. But here in this case, I have applied the mutation. So after the mutation, you have to calculate the fitness value, everyone. Now all of you know that this is 0100. So that's why again I repeat that thing 0100, and that's why according to all of you know this knapsack. So it's a 0100. So that's why the weight is 3 and the value is 5. The weight is 3 and value is 5. Right? So in that way you have to calculate, everyone. Right, so in this way you have to calculate weight and value, everyone. So now when you calculate the total fitness value, so here in this case you are considering, see, here the weight is 3, weight is 9, weight is 10 and weight is 5, and all of you know the knapsack capacity is given, that is 12. So that means all these, what it means? It means that all this population OS1, OS2, C3 and C2 is selected. In the previous case, what happened? One weight is 17. That is more than that. That's why we have rejected. That's why that particular population is rejected. But now what happened? So the knapsack capacity is 12. That means you can say that all these 4 populations are selected, everyone, right? And once these all 4 populations are selected, so what is the total fitness value? So here the total fitness value you are getting, that is 5 plus 17 plus 24 plus 12. So here you are getting 58. But see here, so here in this, after the mutation you are getting, everyone, 58. But see the previous case. In the previous case, what happened? The C4 we have not considered because the weight is what, more than 12. So the fitness value, that is 15 plus 12 plus 24, everyone. So in that case, which value you are getting? So in that case, just wait. Where we have seen. Okay, medium. So in that case, you are getting the value 51, everyone. Okay, so means in the first generation you are getting 51, and after that in next generation you are getting 58, everyone. And what is your aim? And your aim is the which items should be kept in a knapsack, so it will maximize the knapsack value without breaking knapsack. So in the next generation what happened, the knapsack value is maximized. Initially it is 51, but now in the next generation we are getting what, 58, means our in knapsack value is maximized, right? So in this way, see this thing I'll explain about. See, these are first initially we have declared, and then after the all the steps up to mutation we have done. Okay. Now similarly, at last what happened? So after this calculation, what happened? Now again you have start with the next generation, but in that case what happened? Which generation you have to take, everyone? So again now this again sorry again now this whole population you have to consider. Again you have to apply selection, everyone. Clear, everyone? So after this, after the mutation, now this becomes again your next generation. Okay. Now again you have to apply the selection. Then after you have to apply crossover. Then mutation. Again you have to calculate fitness value. Again whatever the population you are getting. Again the whole cycle you have to repeat it. So in this way, in genetic algorithm it works. Hello. Hello everyone. Is it clear to you, everyone? Hello. Is it clear to everyone? Okay. Thanks for replying me. Now, listen everyone. So, this is all about the genetic algorithm. Okay. So, in today's lab, what is your task? So, you have to implement, listen everyone, you have to implement the knapsack algorithm. Okay. You have to apply genetic algorithm concept. Okay. So, in any language, you can implement it. Listen, the program you can implement in any language. Okay. So the problem that is knapsack algorithm using genetic algorithm, knapsack problem using genetic, the same step you have to follow, everyone, right? But implementation in any language you can implement it. Okay. And then after you have to show me the result. If you have any doubt, then please ask me. Is there any doubt in this knapsack problem understanding, everyone? I think all are clear. So you can implement in any language. See, this material I am not uploaded. So right now I am uploading it in Moodle as well as in Drive. I will upload it. Okay, please refer to it. And if you have any doubt, then please ask me, everyone. I am uploading it right now. I have uploaded it in the Drive, everyone. So please refer to it, lab number 9.pdf, that I have uploaded in the that shared folder AI, artificial intelligence. So please refer to it. and also I am uploading right now in Moodle.